Okay, hi everyone. Welcome to today's condensed matter seminar. I am Shulei Zhang, the host of today's seminar. It's my pleasure to introduce today's speaker, Professor Jennifer Carter from Department of Material Science and Engineering here at Case. So Professor Carter obtained her bachelor degree in mechanical and material science and engineering from UC Davis in 2006. And then a PhD from Ohio State University in 2012. Her research focuses on understanding microstructural evolution and the performance of interface-rich materials for extreme environments. She has received multiple awards, including the Presidential Early Career Award for Scientists and Engineers in 2019. So early this year, Professor Carter was named the new faculty director of the Switchlog Center for the Surface Analysis of Materials, which is CWRU's core facility providing instrumentation for advanced characterization and research of materials. So today, Professor Carter and her team members will give us an introduction to the centers, as well as a new fellowship opportunity open to graduate students to apply for instrument time there. So without further ado, Jennifer, please take it away.
Yeah, thank you so much for the kind introduction, and thank you to the physics department for allowing us to come in and talk to you today. We're really excited to be here, and we're going to try to do this on my screen. I have not done many Zoom classes as I might expect with the pandemic, but we will try our best to do so. I'm assuming that everybody can see my screen and we are okay moving forward. So yeah, I'm in the Material Science and Engineering department, and my research is fascinating and interesting, and I'm about the only one that cares about it. So today I'm not actually going to talk about my research at all. I'm here to talk to you about the Microscopy Center and how it might be able to help you with all of your materials analysis, independent of whichever discipline you're in. And so today we're going to, that's not the right button. Oops, there we go. Give a brief introduction to the facilities on campus and where they are and what they do, and then move into the Microscopy Center in general, and then introduce you to the fellowship program, which I'm really excited to talk to you about. And then I will hand it over to Jeff Pigott and John Kim, who are our microscopy experts. I mostly do my job by staying out of their way and allowing them to interact with the student users so that they are the most efficient with everyone's time. So with that, we will move forward. So what are core facilities? Core facilities are shared instrument facilities across the school. They exist in the College of Arts and Sciences and the College of Engineering, as well as in the School of Medicine. And the goal of these is that they benefit researchers across the universities when we have instrumentation that has sufficiently more bandwidth than any one researcher can use in their own research. And so they provide equipment, training. We can also do some work for service and for hire for both researchers that need work done very quick. So say for like a DARPA program or even industrial collaborators, as well as providing expertise for student researchers to come in and question and ask questions about techniques and different analysis. So we have core facilities across the entire university that accommodate and account for materials processing and analysis. And so what does that look like here on campus? So here on campus, we have 13 or so facilities. Most of them are in the College of Arts and, in the College of Engineering. But the Moore Center, which many of the physicists know and love, as they should, is housed in the College of Arts and Sciences in the physics department. And then the NMR facility, for example, is co-owned and run and organized by the College of Arts and Sciences, the School of Medicine, and the College of Engineering as well. So you can find lists of these core facilities. There is research.case.edu, which has a fairly outdated or updated, depending on which company line you believe, list of those core facilities. And then on the microscopy website, which is the Swagelok Center for Surface Analysis and Material, or affectionately known as CSAM, I have provided a list of all of the cores that I know of that are useful for material synthesis, and characterization of structure, microstructure, and ultimately performance of materials. So the CSAM facility provides equipment, training, and services and expertise in microscopy, surface analysis, and the analysis of structure and properties. We have somewhere between 11 and 14 instruments that the engineers and scientists maintain depending on any given month. We've had a lot of movement of equipment in the last 2 years, so I'm not sure I actually have a number. Jeff is, of course, the executive director of the facility, and he'd have a much better idea of what equipment we actually have working at any given time. But we provide a variety of services, and the people that are providing the expertise are as follows. And we're going to let them talk about their different techniques today. We're going to hear from Jeff Pigott, who's the executive director. He's got a background in geology and inorganic materials. And then John Kim is going to talk about analytical techniques and how he uses those for trace element analysis. We also have Nicole Hoven, who works with us part-time. The rest of the time, she is in the microfabrication lab. And so on staff, we have someone that is an expert as well in thin processing and what the capabilities on campus are. So that's a helpful collaboration between the two centers. And then just last week, we are excited to announce our newest scientist, which is Tucci, and she's joining us from Iowa State University, where while getting her PhD there, she was running the microscopy lab for the graduate students. So we're really excited to have her on the team and how we might be able to use her expertise in more efficiently training users in the future. So what you really want to know is what is this fellowship application that I'm talking about? So as I alluded to at the beginning of this, we've had a lot of movement and shaking and changes in the microscopy center in the last year. We have brought on a new SEM, which is the Thermo Fisher aprio, which Jeff is going to talk about today. And in the process of doing that, we have already sold off 4 instruments, so those no longer exist, and are in the process of selling off 6 more in hopes that we bring on new XRD capabilities to support the thin film researchers we have on campus because our techniques and our tools are incompatible with those user space. And so because we've had a whole new team of researchers come in, both Jeff and John started at the beginning and middle of a pandemic, and we have new tools. We'd really like to get out there and meet the new student users because we haven't really engaged much with the community in the last 20 months or more because there was a pandemic. Maybe that was funny, maybe that's not funny. But anyways, we're going to start a fellowship program and we're going to kick off the first round of applications in November. And depending on how successful these are and how long funding holds out, we will continue to do these on a rolling basis. Somewhere between 6 and 9 months is what I would expect. But we fashioned this application after the general user proposals used by the national labs so that you can get access to user facilities. So if any of you have used those in the past, it'll look very familiar. And the goal with this is to get students to talk with our research engineers and see what kinds of experiments might be able to bring their research to that next level and do something that was never in their scope of work, but could be really interesting. We envision that the scope of work is somewhere on the order of like 2 to 6 hours worth of microscopy time. It may make a figure in a paper or maybe the foundation for future work in a proposal. The proposal application is only open to PhD researchers at this point in time because of where the money comes from, but that is what we are doing. So it requires an abstract, general information about where the student comes from and what your scientific goals are, as well as what you think your proposed instrument needs are. I highly recommend talking to our research engineers to apply to this application. And so with that, I'm going to let you begin to talk with our engineers. And so we're going to transition now to letting Jeff Pigott have the virtual floor and talk about our aprio machine. Jeff, do you want me to run the slides or you got it? You got it.
No, I'm doing it. I just did the share screen. Can everyone see my screen and hear me?
Yes, yes, we
Okay.
can.
Oops, sorry. Let me just, I was at the wrong slide. There we go. Yeah, so thanks, Jennifer, for the introduction to the center, and thanks everyone for attending the Zoom meeting. This is the first Zoom seminar I've given, so hopefully it goes well. And to just clarify what Jennifer was saying earlier is that we currently have 14 instruments that are functional, online, being used regularly or could be used at any time. So she was pretty close in the 11 to 14 range. We're on the high end of that. So I'm going to talk about our new Thermo Fisher aprio that was installed in installed in March and April of this year and officially signed off on in May. And since the beginning of June, we've been training users on it. Almost entirely student users, ranging from undergraduate to PhD, and also postdocs as well. Over the summer, we've trained 25 users. 8 of those are now independent users, and one of them is what I would classify as a super user, and that's Laura Wilson, shown here. So the aprio, the new aprio has a lot of features that make it special. One being that it's excellent at imaging insulating samples without the need to apply a metal coating to reduce electrical charging. So that can be accomplished either at low voltage and current in high vacuum. And it's also a variable pressure SEM. So we can go into low vac mode, in which water vapor then is the charge compensator. It's decked out with pretty much every possible detector and analytical tool. So we can do, in addition to basic secondary electron and backscattered electron imaging, we can do EDS, electron backscatter diffraction, or EBSD, cathode luminescence detector, and we can do TSEM, or transmission scanning electron microscopy. And I'll talk about all of those techniques in case any of them are unfamiliar or interesting to you. We also have some advanced software that allow for more advanced techniques, such as the Pathfinder software for quantitative EDS and also EBSD, and then the MAPS software where we can map through imaging. We can map samples on the aprio and, for instance, move them to the Helios to do further focused ion beam transmission electron microscopy prep. And also we can do automated sample mapping and stitching, which has been used quite a bit by Professor John Lewandowski's group and his students to map fracture surfaces and then do it automatically. And that's the MAPS software. So some examples of some of these techniques that I was referring to. Here are some examples of high resolution imaging done both on samples that were synthesized in the Moore Center. So on the left these images were taken with me by a first year undergraduate student, and this really highlights the ease of use of the aprio. It has a lot of features that allow for rapid student training. They can get, in this case, very high resolution imaging safely without damaging the instrument, and also quickly. They can get trained up pretty quickly. So this is gold titanium on glass substrate for imaging the grain morphology and grain size. And then what's the feature that we really want to highlight can be demonstrated on the right. So this is a perovskite sample on glass, again synthesized in the Moore Center over the summer with by Ina Martin and one of her collaborators. And this is an insulating sample on an insulating substrate, and this is an image of the grains to get the grain size and grain morphology without applying any conductive palladium coating. So if we were to apply palladium to try to image this, it would most likely cover up a lot of features of the thin film. But without that, just by going to low voltage and current, in this case, 1 kV and 13 picoamps at 120,000 X, we can still get very good images of the grains. In addition to imaging, we can do EDS and we can do quantitative EDS, whether it be standardless or standards-based quantitative EDS using the Pathfinder software. And this is an example of some work that I've been doing in collaboration from a microscopy perspective in collaboration with the Cleveland Museum of Art, where the conservation group is restoring a 17th century Italian painting. And in order to do that restoration, they really need to know, what if there are fossils present in the paint layers, or if what the mineralogy is of the paint layers. So in this case, this was a polished paint section that we did do palladium coating on because we didn't expect any of the elements to interfere with that. So that was the appropriate technique. And with the Pathfinder software, we can do advanced data processing and analysis. We can do maps, lines, points. In this case, this is an example of a point spectrum to, we determined that this, what mineral this is, and then this is useful to them in order to restore the painting. We also can do cathode luminescence to get a sense of the chemistry, the chemical distribution in a sample. So with cathode luminescence, when a sample with a band gap is excited by an electron beam, electrons from the valence band can be excited to the conduction band. And then when they relax back down, they may be trapped in electron traps. And while they are trapped there, they give off visible light. Think about photons of visible light. And this is based in band theory, but with the cathode luminescence detector, we can get phase identification in multi-phase or inorganics that have similar structures. It's also can be used to determine if there are trace elements or trace impurities or defects and where those are distributed. And this is at below the detection limit of EDS, so below approximately 0.1 atomic percent, although it is qualitative. So with the CL detector, it's just, you're just going to image, it's just going to be imaging. There's no spectrum to actually identify what the trace impurities are. We have other techniques for identifying that if you're interested, but in this case, it can be used to visualize rapidly where there are impurities or defects and how they're distributed throughout your sample. And in this case, this is an image taken on the aprio of a zircon or a zirconium silicate. In this sample, again, this is done in low vacuum. So this is insulating sample mounted in epoxy, no metal coating. And you can see the zoning of trace elements that are occurring throughout the sample. So these concentric rings can be used by geologists for age dating of minerals or determining different occurrences of how this mineral formed. So this could be applied to, semiconductors or other insulators as well. We have a transmission scanning a TSEM detector, and in this case, so this is kind of this is a rapid version of TEM. So if you have a need to get TEM images, but you don't need atomic resolution, or you want to screen multiple samples before you actually go and get the more expensive TEM time, which is usually harder to come by, you can screen and really get the samples of interest before your real TEM time. But basically you can load a TEM grid or a focused ion beam grid into the sample holder, and then the detector comes in underneath the sample, and you can shine the 30 kV electron beam, as opposed to a TEM, which is 200 or 300 kV. You can shine the 30 kV electron beam on the sample and get the same type of images as you would on a TEM. So bright field, dark field, high angular, annular, dark field. So these are the three basic types of TEM images. In this case, this is a polystyrene sphere on top of gold nanoparticles. And you can, so in this case, you could get a pretty good idea of the average grain size of the nanoparticles without actually, going to a full TEM. But in this case, you would get a better estimate than just regular high resolution SEM. We can also do electron backscatter diffraction in which case you can get the crystal orientation and phase identification by taking a polished sample and tilting it at 70 degrees and detecting the Kikuchi diffraction. However, there are some constraints on this. So on the right is a view of the sample chamber with the sample tilted up at 70 degrees and the detector coming in here. There are some constraints in that you really need a defect-free sample, which is it's very important and it's challenging to accomplish. So it needs to be, chemically polished or polished down to colloidal silica or ion polished. That's because the signal, the diffracted electron beam is coming from just the very near surface. So any sort of surface defects will spoil the pattern. And also insulating material can be very challenging, but this can be done in low vacuum mode or the very thin carbon coating. And so this is the type of data that one would get from it. So this is data acquired by Laura Wilson on some additively manufactured nickel alloy, looking at, so you can visualize the grains and get grain size, grain orientation. You can see if there is texturing or preferred orientation. And again, this can be applied to predominantly metals, ceramics, geological materials, and you can get information in addition to, you can get phase ID, grain size. Look, you can visualize grain boundaries, twinning, texturing, strain. There's a lot of information that can be extracted from EBSD. And then for the final two slides, for the aprio, I want to highlight some of the in situ capabilities that we're developing, and that Tuche will be really taking the lead on, and that's developing in situ electrochemical experiments using the Hummingbird liquid cell, where one can use the TSEM detector to image wet samples, do electrochemistry in situ hydration, so we can flow gases or water around a sample while imaging it. And it's based on these chips where you can have window chips to recreate, you, for instance, put in a wet sample that then is isolated from the high vacuum SEM chamber. So it forms an environmental cell. So you can image a sample in its native environment, as well as you can heat it, apply electrical biases, do electrochemistry. And in addition to the Hummingbird system that we're currently in the process of purchasing and then we will be installing very soon, we currently have a high temperature stage where we can heat samples while in situ while imaging. Where we can do secondary electron imaging up to 1100 C. We can do EBSD up to 900 C, and then backscattered imaging or EDS up to 400 C if you want to see chemical changes. And this is an example of melting of gold wire in the SEM. So the type of applications that this could be used for would be looking at phase transformations, recrystallization, grain growth, oxidation, and yeah, this can all be done in situ. And I will be happy to, if you have any interest on learning more about these techniques or how they could be applied to your research, or if you want to discuss how to implement and experiment, you can feel free to contact me and or Tuche. We'll be happy to discuss that with you. Thank you. I'll pass it on to John now for Auger spectroscopy.
Okay.
And I'll stop sharing.
Hi everyone, can you see my screen and hear me okay?
Yes, we can hear you and see your screen.
Okay. Hi, I'm John. I look after the three analytical tools at CSAM. I realize I'm talking to physicists who are probably experts on XPS and OJ already. So bear with me. Hopefully there are new students who are new to the technique that may benefit from the presentation. So the three instruments we have are OJ electron spectroscopy, where we're using the electron beam to generate OJ electrons and analyzing those electrons to determine the chemical state and elemental composition of the sample surface. We have the XPS, where we use the soft X-ray. In our case, we have the aluminum K alpha X-ray, and we analyze the photoelectrons and OJ electrons that come off the surface to get the similar type of information as we do the OJ. And we have the time of flight secondary ion mass spectrometry, which I hope is a new technique for you, where we use the ion beam to generate secondary ions, and analyzing those ions, we can determine what elements we have, as well as the isotopes, and also get some molecular structure information. So all the three instruments, they are surface analysis techniques. So we are probing the top few nanometers of the sample The techniques are equipped with sputtering guns. So if you wanted to sputter and do a test profile to poke deeper into the sample, we're able to do that as well. Just to go over some pros and cons of each instrument. Top SIMs, you're not limited to what elements you can analyze from the periodic table, but you do have some limitations for OJ and XPS. Top SIMs has a higher detection limit than OJ and XPS. In terms of lateral resolution, because you're using electron beam for our OJ spectroscopy, that has the highest lateral resolution, followed by top SIM and then XPS. And I guess the next 2 points are, I guess, the important ones. OJ and XPS are quantitative. Top SIM is not considered a quantitative technique. It could be semi-quantitative depending on the sample system that you're wanting to analyze. And another important point is that XPS and top SIMs, we can analyze conductors to insulators, but with the OJ, it's mainly applicable for conductors. Some semiconductors we do and we can analyze, but does require some attention when you're trying to mount the sample. So having said all that, what are the main uses for each instrument? With the OJ, obviously we're doing small area analysis, looking for elemental composition and chemical state information. We can do the same sort of analysis, get the same type of information with XPS. The advantage is that we're able to look at insulators as well. With the top SIMs, because you have a high detection limit, it's good for trace element analysis. You can also probe isotopes of the elements that are present, and it can be used to look at molecular species as well. So, and all the 3 instruments can do imaging and also test profiling as well. Sorry. I don't know what has happened. My screen just froze. All right, so what's an OJ spectroscopy? I think many of you know this already, but we use an electron beam to knock out an electron, and the hole that's created in the K shell in this case is filled by an electron in the L1 shell, and that energy release is used to kick out an OJ electron from the L23 shell. And the energy of the OJ electron is shown here in this formula. So on the right is the typical OJ spectrum that we get from copper standard. And you see in the magenta color spectrum, it is hard to sort of make out where the peaks are because usually all these spectrums are all superimposed on high background. So you can sort of magnify things a little bit, and you see the red spectrum. You start making out the copper peaks. But typically, because it's hard to see it in the integral mode, we do differentiate the OJ spectrum, like shown in the green color here. To identify the peaks better. So one example of, I guess, where we use the OJ spectroscopy is when we're looking at the microstructures for 7075 aluminum alloy. So our OJ instrument does have scanning electron beam, so we can obtain SCM image. And from the SCM image, we do have these round shape particles and irregular shape particles, which have different compositions that we'll analyze with OJ. So for example, this round particle has aluminum, magnesium, and copper composition. And furthermore, what we can do is we can use the OJ spectroscopy to determine the chemical state of the magnesium, shown on the right here. So looking at the peak positions, peak shape, and relative ratios of the peaks, you can sort of assess the chemical state of magnesium as the sample underwent different treatment. Second instrument that we have is the XPS. We're using a soft X-ray to generate a photoelectron, and the energy of the photoelectrons we reach binding energy by this relationship here. And we can also get X-ray induced OJ electron in this case. So those who haven't come across XPS yet, on the left, we have the example of what an XPS survey spectrum looks like. It's a plot of intensity versus the binding energy. where we're scanning a wide energy range. And we can determine what elements are present and quantify those elements. So we have oxygen, carbon, silicon, aluminum detected for this sample. And if you wanted to sort of zoom in and look at the chemical state of aluminum that were present, we do a high resolution scan. On the right, you see that the aluminum consists of metal and oxide forms, and we can quantify those as well. I just wanted to give you an example where sometimes just a photoelectron peak itself is not enough to differentiate between the chemical state of an element. So example here is for copper. On the left, you see the copper 2p photoelectron peak, where you have the cupric oxide in blue, copper 1 oxide in green, and the copper metal in red. And you can see that the copper 2 oxide can be differentiated from the copper 1 and copper metal because the photoelectron peak position is different. And you also have something called shakeout peaks. But just using the photoelectron peaks, you can't differentiate between the copper 1 oxide and copper metal. In this case, you can use the copper OJ to differentiate between the copper 1 and copper metal species. The third instrument we have is the TOF-SIMS instrument. So here we are bombarding the sample with a primary ion beam. We have a gallium source as well as C60. This leads to collision cascade and emission of number of particles, one of which is secondary ions that we're interested in. And these ions are analyzed according to their mass to charge ratio, and you get your typical mass spectrum, intensity versus mass to charge ratio. So with TOF-SIMS, I want to sort of highlight the imaging capability of the instrument. So here we're looking at the asbestos sample. On the left, you have the 2D elemental imaging that was acquired with TOF-SIMS, where you have the total ion imaging as well as the imaging due to different elements that are present in the asbestos. On the right, we have the 3D images that were acquired for the asbestos samples that underwent different treatment. And you do see that there is a good contrast that's observed among the samples. And there's, I guess, two ways to do the 3D imaging in TOF-SIMS. One is just to continue the acquisition. So if I was acquiring 100 microns by 100 microns area, one complete scan of that area would be my first layer. And then second complete scan with my second layer. I can compile them all together to generate a 3D image. Another way is to do a depth profile. So analyze, sputter, repeat that cycle, and then you can also generate a 3D image that way. So in this example, the images were acquired without the sputtering. And lastly, I wanted to show you an example of depth profile that was acquired with TOF-SIMS. Here, we're trying to monitor how the two isotopes of oxygen, oxygen 16 and 18, varied with regards to depth for aluminum oxide layer. So you have the count on the y-axis, x-axis is the time scale, which is a sputtering time. And once we know the sputter rate, we can convert that axis into depth scale. So we found that the oxide layer that was probed in this case about 3 microns. And you do see sort of a good, nice profile of the oxygen 18 and oxygen 16 species. And again, with this, I could generate a 3D image, but I could also obtain a cross-sectional image of each species shown here. And you could do the same profiles for XPS and OJ as well. So if you have any questions, please feel free to ask. Hopefully, I'll be able to see some students in person to help out with their analysis needs in the future. Thank you.
Thank you so much, John. I think that concludes the information that we have to present with anyone, and we can go ahead and open it up to question and answers, either via the chat function, or if you are in a place where you can unmute your microphone and not have either small children or dogs or chickens interrupt too many times. So.
Any question from the audience?
Sure, I think I saw Harsh's hand go up first.
Okay, but I'm a theorist, and my question is actually not about the instrumentation, but I was just curious about that art, flake, the painting analysis that you've done. I was wondering what kind of sample you use for that. Is it like a flake from the painting, or do you actually stick the whole thing in there, or how does it work?
Actually, so the painting is, it's a large painting. I mean, it's wall size. I mean, it's a old large painting. So it's just he just takes, so Dean Yoder in the conservation, he's in the painting conservation. He does the paintings in the conservation group at CMA. It's just a very small flake. I would say a millimeter or two across, and maybe 500 microns thick, maybe a millimeter thick. And then it's mounted in epoxy and polished. So he just, in that flake represents all of the layers of the painting. So the paint layer, in this particular painting, there's a lead paint layer, and then the ground layer. So it's kind of it's a whole cross section of the painting. And so he takes, I think he has about 15 locations he'll take. So he'll make 15 cross sections, give or take, from different areas, different regions of the painting that are, representative of the different paints used.
Okay, great, thank you.
Cassie, you have a question?
Yes. Wow, that was a lot of information. So I'm really glad we have a recording of the presentation. Thank you so much. I'm really eager to follow up with some of your new capabilities with my own research, but so I'll do that later. But I'm also intrigued about the possibility of biological samples. And while I don't have any direct interest in that, I wondered if you could say a little bit more about that application for your facility.
Yeah, I guess, do you want me to answer that, Jennifer, or do you want me to? Yeah, I took out all of the biological slides from this talk because I thought I should focus on solids for the physicists. But yeah, we certainly can do biological samples. The slides that I had were on some imaging of fungal fibers and imaging of blood cells that were, kind of wet. So we do this instrument's really actually fantastic for imaging soft biological materials. As far as the aprio, John can also talk about biological applications. But the low voltage and current and the low vac mode, and then the hummingbird cell that's coming online, we can certainly do imaging of biological materials, and we do. So if you're interested,
Yeah.
we can do EDS on biological materials as well.
Yeah.
John, do you want to talk about some of the surface applications of biomaterials?
Yes. Top sims is a very good technique to look at biological samples because we're able to analyze molecular fragments. So I've studied a lot of leaf samples where you're studying the waxes materials on the leaf. And it doesn't cause a lot of damage to the sample itself, but you're only probing the few atomic layers. And as long as you see a peak that's due to a molecular fragment, you can use that to image it or do anything you like with this. So it's a very useful technique for biological samples.
So I just wanted to, thank you very much. I just wanted to follow up by saying that one of our important thrusts in the physics department is biophysics, both theoretical and experimental. And we plan, I think the plan for the department is to expand that area. So just wanted you to keep that in mind. Thank you so much.
Yeah, on that regard, anybody that is interested in the biologicals and talking with me, we are currently in negotiations with Hummingbird Systems, which makes an environmental cell. And the goal of this system would be to be able to take wet samples or electrochemical type reaction experiments and be able to do those both in the SEM and then subsequently when we get our new XRD system up in line, which we are working towards doing, to be able to run those same experiments in the XRD, because sometimes you need the crystallography and sometimes you need to see it. So if anybody's interested in that, I'd be super happy and excited to talk to you to make sure that we spec the system with the types of reactions people are interested in looking at. That is something we want to look forward. And then in that, we're working towards getting a new XRD system. As you all, as at least the faculty are probably aware, our XRD systems in the microscopy facility are easily 20 years old, which makes them difficult to run and difficult to train student users on. So it's hard, they don't get to use it independently. And that's sort of a shame considering we're training new users and training new engineers and scientists that they don't get to use the instruments. But if anybody is interested in the techniques for thin film analysis and or SAX and wax capabilities, I'd be really interested in knowing what you need to make sure that we spec the right equipment for that. Because we can only be a user facility for the users if I can get you guys to talk to me. And if not, I just have to make assumptions and hope that I can make a halfway decent guess. But that's where we're at. So the aprio in its standard configuration can look at semi-wet things, but it's mostly solids. When we want to go to truly wet chemistry, we need to move towards the Hummingbird tool. And I would be happy to find you a link to that. This is just a off-the-shelf tool. Let me make sure that I get the right one. It is. But this allows us to be able to run 2 liquid flows into a solid chamber. And Hummingbird makes over 60 different pre-packaged MEMS devices where you can deposit your samples on them. So if you needed a heating stage, they've got that one already built to accommodate the current voltage that come through the sample, or if you just want to be able to look at things in between 2 electron transparent films, those are also options. So.
Great. Any other questions from the audience? Okay. If that's not the case,
maybe I'll have a question.
I would.
So Jennifer, nice talk, but and again, you know, I'm a theorist, but I'll ask a little bit different question for you as a director. You mentioned that some of these equipment is old and maintenance is a problem. So what are your plans in the future for how to maintain this system? And I'm also thinking like, okay, how do you rate our system compared to some of these core facilities at some of our peer institutions and so on? And I'm asking these questions because we have a new president. And so he